So we're going to continue our series of lectures on training. Everybody, laptop shut. No exceptions. You're only going to use your laptop for quizzes, right? Can you shut it properly? Thank you. You lady at the back, do you mind shutting your laptop? Everybody, please shut your laptops. We're going to continue our series of lectures on training. We're going to speak about optimization. Asmita, what was the last topic we were discussing? We spoke of backprop, didn't we?
Yeah,
and then we spoke of, what else did we speak of? Can I see your name tags? Yes. What else did we speak of? Yeah, Digant? Convergence. We spoke of convergence, and we spoke of problems with convergence, and we spoke of the fact that part of the reason we have problems with convergence is because the gradients that we compute can be noisy. So we also briefly mentioned momentum methods towards the end of the class to see how you could smooth out these gradients, right? And so here's the recap. Here's what we've seen so far. Neural networks are universal approximators. We must train them to approximate any function. They are trained to minimize a total error on a training set. But the error is your loss function. And we do so through empirical risk minimization. We also saw that we use variants of gradient descent to do so, where the gradients are computed using back propagation. But you might use additional heuristics like computing running averages to smooth out your estimate for the gradients. So we saw that vanilla gradient descent could be too slow or unstable. Better convergence can be obtained using second order methods that normalize the variation across dimensions. Where in the last lecture did we discuss this, Harini? Does anybody remember where we discussed this in the last lecture? We didn't discuss it, right? It's in the slides. You aren't paying attention. Anyway, we also saw that adaptive or decaying learning rates can improve convergence. Why was that, Giovanni?
Because can otherwise can also smooth convergence.
There was a different reason. Why was that, Krish?
We start out with a higher learning rate, so it can escape the local minima and go into the bigger world.
If you start with a large learning rate and shrink it, you can escape local minima and sort of fall into a better optimum, right? And methods like one of the reasons we saw for problems with convergence was that every dimension was assumed to have the same learning rate. We saw that this was not the right thing to do. And so methods like rprop could help estimate what was the best thing to do in each direction independently. And momentum methods, of course, basically smooth out the estimate of the gradient itself to make things better. So moving on, today we're going to be talking about incremental updates. We're going to revisit trend algorithms. We're going to talk about generalization and a few tricks of the trade in today's class and Thursday. So start with this. Here's how we formulated training. You were trying to estimate some function. This function was unknown. But what we did have was some input-output measurements from this function. And so we tried to find a function that computed the correct output for every one of these inputs. And the hope was that if you did this properly, then the function is maybe going to capture the network is maybe going to capture the correct function everywhere as well, everywhere else as well, right? So the way we did it, you'd start off with it was a gradient descent approach. You start off with an initial estimate for your network. And the initial estimate models some other function, maybe the one shown by the red line. And then when you compute the error, you're going to find that you're making errors at every single point. So your update tries to minimize the total error across all of your training points. So the update would say, try to increase the function value at these locations, maybe push it down at these locations, and push it up at this location all at the same time, because you're minimizing the error over all training samples. And then when you do that, you get a new estimate for the function. And then the next update is again going to try to correct the error at every location, push it up wherever you have those green arrows, and push it down at the locations of the red arrows. And this continues at each step. You keep trying to correct the function everywhere at every single training instance to try to make it match the actual function, at least at those training samples. Now, what is the problem with this kind of computation? What would it be? Computationally, what is the issue?
It updates after looking at all the
You'd have to look at all of the training samples before making any update. That's going to be expensive, right? So this is what we will call a batch update. And the problem here is that you must process all of your training points before making a single adjustment. And this can be a bottleneck. So here's your first poll. Have the timing? Okay. Super slow. Okay, 5 seconds, guys. Set a beat, a timer. All right. So let's close this. We'll run out of time otherwise. Can someone on Zoom? Is there anybody on Zoom? Can someone on Zoom tell me if the first statement is true? Someone on Zoom, or is there nobody on Zoom? So technically, everybody on Zoom is absent.
I'm here.
Okay,
I'm
what is
here.
it? So what is the answer to the first? Is the first statement correct or wrong?
Correct.
Correct. You guys agree? What about the second one? Correct or wrong? Someone at the back. Maybe you can tell me. Raghav, is the second statement correct or wrong? And Kofi, what about the third? And Simrit, the fourth?
The fourth is also correct.
They're all correct. They're all correct. Thank you. Right? So the actual loss function that you're trying to minimize is the expected divergence, right? And the loss that we compute, which is the empirical risk, is just a proxy for it, which means you actually have to minimize the error at every training point. You need batch updates. Batch updates minimize the total loss over the entire training data. So they optimize the actual loss function, which is a proxy for the actual target, the actual objective, right? And I'm sorry. And they require processing the entire training data before you perform a single update. So this is expensive, right? Now, here's an alternative. Remember how you sort of, if you want to shape some putty into some shape, it's not like you suddenly sprout many arms and you shape it all at once at every point. You sort of push it in individual locations, one finger at a time. And when you push it down somewhere, maybe it pops up somewhere else. But if you do it gently enough and a sufficient number of times, eventually you're going to get the whole thing shaped up, right? So we can do the same thing here. Instead of trying to fix the function everywhere all at once, we can adjust the function one training point at a time. You keep the adjustment small, just like in the case of the putty. If your putty is off from the target shape by a large amount at some point, it's not like you push it all the way down. You got to do it a little bit at a time. Otherwise, it's going to keep sort of reacting in strange ways, right? And so maybe you pick up one sample. And then at this point, the function is off. So you make an adjustment that pushes the function up at that point. You're not really sure what happens elsewhere. But if you keep it small enough, maybe things don't become much worse at other locations. And then you pick up some other point, and then you push the function up over there. And then a third point, you push the function down over there. You can do this one sample at a time. And if you do this carefully enough and a sufficient number of times, eventually you hope to get the entire function in the shape that you wanted. So the key here is to keep the adjustment small at each point. And eventually, when you have processed all the training points, you would have adjusted the entire function. And the interesting thing is that if I make an adjustment at each of the training points, one at a time, the final adjustment that you can make can actually be greater than if you looked at all of them all at once. Because you made so many small adjustments, the cumulative adjustment could be much greater than just making one little batch adjustment. And so here's what the pseudocode for this is going to look like. Remember how we perform batch updates. You went over the entire data, then you computed the gradient at every training instance. You computed the average gradient across all the training instances, and then you made your update. Here, it's going to be different. Here, you would be going over all of your training instances, and then after each training instance, you would be computing the derivative of the divergence for that one training instance, and immediately make your update. So you're going to make your updates after every single training instance. Make sense? Right. Now, when you do this, it's not like you're just going to go through the training data just once. You're going to go through all of your training instances, make minor adjustments at each training instance once, then go back and repeat the process, and then go back and repeat the process yet again. So each pass through the training data is going to be what you would call an epoch. So if you have T training samples in a single epoch, you're going to make T adjustments, and then go back and do it all over again. So in your pseudocode over here, if you look at what's happening, you go through all of the training samples, you make your updates, but then once you're done going through all of the training samples, you're going to go right back and repeat the process. So the outer loop represents an epoch, and each of the updates within the inner loops is a single iteration of updates. Now, there's some caveats. You can't just do this carelessly. To give you an idea of what can go wrong, consider this example. I have 4 training instances, and then I have a target function, which is shown by the dotted line. And maybe the function that my model represents can only represent somewhat of a curve. So over there, your best approximation for the curve is going to be something fairly horizontal, right? But then if you went through the training samples left to right, then each time in the beginning, you're going to sample the first 4 training instances. Each of them is going to ask you to push the function down over there. So the function would go down and maybe become something like this. But then you go to the next set of training instances, which are to the far right. And those are going to push those down, and then it's going to go right back to where it was in the first place. So when you do this, you're going to get cyclic behavior, right? What would be a good solution for this? Obviously, this is a serious problem. So how would you resolve this? Yes? You would want to randomize, right? Shuffling the training data as a way of randomization. What you'd really do is go through the training data randomly, and that's going to give you more convergent behavior. So maybe you pick up that training instance and push it down a little bit. And then you get a new function. Then you sort of randomly pick a completely different training instance, which could be one to the right, and then you push it up over there. And so you'd have to go through the training instances randomly. If you didn't go through them randomly, and if you did it in the same order every time, then you are going to get suboptimal and possibly cyclic behavior. So here's what now. One way of picking random points to update is to simply shuffle all of your training data. If you shuffle it and then go through it sequentially, this is the same as picking up random points. And the order in which you're going to pick up these points is going to change from epoch to epoch. Otherwise, you still have the same cyclic behavior, right? So within each epoch, the first thing you would do is to randomly permute your training data. Just shuffle them, and then go through all of them to make your updates. Any questions? Yeah.
If your model had sufficient capacity, is this cyclic behavior still an issue?
It's still going to happen, right? Regardless of what the capacity is, it's currently got some shape, you're making some adjustments. Think of it as putty, right? Your putty can be arbitrarily soft. You can make anything with it. But if you keep pushing things in the same order each time. When you push something here, something pops out elsewhere and vice versa. It's just going to happen. So any other questions? Okay. So the story so far, in any gradient descent optimization problem, presenting training instances incrementally can even be more effective than presenting them all at once for two reasons. One is computational, and the other is that when you go through the training data once, you're going to make many, many more updates than if you performed a single batch update. Now, this is a tall claim, but I'll show you why this is the case. And for this, there are a couple of caveats. One of them being that the training data must be provided in random order. There's another that I will talk about in a bit. This method is called stochastic gradient descent. It's stochastic because you're randomizing your training data from epoch to epoch, and it's gradient descent. You're doing this one sample at a time, right? Now, this general technique that I just spoke of, this applies to any kind of optimization problem, and clearly it also applies to neural networks. So why would this process of incremental updates work, and what would the conditions be for this to work? For the why, let's just consider a very simplistic problem first. Now, let's take an extreme example, right? Typically, when you compute your batch gradient, the batch gradient is the average of the gradients over all of your samples. So the gradient, as you know, points in some direction. So every single training sample is going to point, the gradient for every single training sample is going to point in a different direction. And the batch gradient is the average of all of these gradients. So you might have, for instance, all of these little blue arrows as the gradients from the individual training samples. And the red arrow is the average. That's the direction in which you want to, these things are pointing in the negative, towards the negative of the gradient, but that's the direction in which you want to move your estimate to improve the model, right? Now, what happens is that this average points in the net direction of all of these samples. Consider a case where all of your training samples are exactly the same. So if all of your training samples are exactly the same, how much does the average gradient differ from the gradient for a single instance? It doesn't differ at all, right? So if you were performing batch update versus stochastic gradient descent, what would the benefit be for the one versus the other? What is the average gradient for all of these guys? The average gradient for all of these is just this one, right? So after having processed all of the data, you're going to make the same update that you would have if you had made an update after just a single instance. So clearly this is highly suboptimal. Whereas if you were making an update after every single instance, even though the actual update may be smaller, the net is going to be much larger than if you had just waited to process all of the data before making a single update. Now, this is obviously the case if the data are all clumped together at the same location. But if I perturb the data a little bit, and they were not all identical, but more or less close to one another, would the same behavior still be expected? What do you think? So suppose you had something like this, where they're not exactly all the same place. Would you not expect very similar behavior? That if you made an update after every instance, you're still going to get greater net updates than if you waited to process everything. You would, right? And so, guys at the back, do you mind shutting the laptops? Thank you. So, shut it in the forward direction, unless you're looking at the slides. Okay. So this same principle still holds, even if the data are just very close to one another, right? And when would it sort of break apart? What is the worst case for this? Can you get your name tags out? All right, I'm just, Ritvik, what would be the extreme case of this? When does this idea fall apart? So we're saying that when all the training data are all together, then the incremental updates are more effective than batch updates. If they are close by, you still expect that to happen, right? As the data get more and more scattered, where would it sort of, where do you think the benefit is going to vanish? So we are speaking about the distribution of the data, right? So somebody else want to take a guess? When, yeah. Thank you, exactly, right? If the data points are scattered, then what one data point, the update that one data point recommends is going to be very different from the update that the other data points recommend. And so that's when you'd expect that the gap between the two would kind of vanish, right? So nonetheless, you can expect that if you make an update after every single instance, you might actually end up converging faster than if you waited to process your entire training data before you made an update. So yeah, that's the general principle. But when does it work and what are the considerations? Let's take a slightly closer look. Further, the first issue we'll look at is the learning rate. I said there were two caveats, right? One is it had to be randomized. The second one is the learning rate. Suppose I have all of these as my training data points, and I'm trying to fit a linear regression. The red line is clearly the linear regression. But then, if I were making an update after every single instance, what would happen? If I started off with the correct regression, then, so I have something of this kind. I have all of my training data points. And let's say I initialize my model with the correct regression. Then if I start off with considering this data point, what's going to happen to my estimate? It will shift, right? It's going to maybe go through that data point. Then I randomly choose this data point. What's going to happen? It's going to shift. So as I keep going through the data points, is it ever going to give me the correct answer? You're always chasing the latest data point, right? And so the answer is going to keep bouncing around. So what would your fix be in this case? Yeah, you're going ahead a little bit, but that is not the answer. Yeah. The learning rate, please speak up. Yeah. You would have to decrease the learning rate. So as you go through the training data points, each time the step size that you choose for your gradient descent will have to change, decrease a little bit. So that in the limit, when you've sort of got the right line, even though you're sort of cycling through the individual data points, the nudges that they're going to suggest are so small that you're not really going to kill your answer. And so this is what you would need to do. You would actually have, this is the same pseudocode as before. There are two key points. One, of course, is that the data have to be permuted from epoch to epoch. The second is that the learning rate must shrink with the iterations. At each iteration, you're going to require a smaller learning rate than what you had in the previous iteration. So what would the restrictions on the rate at which the learning rate shrinks be? Can anyone guess? Can it just shrink arbitrarily fast? Can it shrink very, very slowly? Take some guesses. I'm asking you to, say something based on your intuitions. Yes. Based on the but the loss itself doesn't tell you anything about the gradients, right? That's a reasonable guess, but you're looking, speaking of looking at the data points to decide. Can you speak of some generic principles?
Small at first, large at towards.
Small at first, large at later is going to do the exact opposite of what you wanted. Right? Large at first and small later, but how fast? So there's actually a clear idea. There's a definite principle to this. Now, suppose I have a cap on the slope of the loss function. So the loss function has a maximum slope. If the loss function is infinitely steep, you're not going to be minimizing it anyhow. You need loss functions which are well behaved. So let's say my loss over S some, how do you write delta, right? Lesser than some delta, always, okay? Then I start off, let's say this is my initial guess, W0, and let's say this is my optimal value, okay? Based on these, what can you say about the convergence or the manner in which the loss function itself, the learning rate changes? At any step, if eta is the learning rate, what is the largest step you're going to take? Yeah? So, but what is the largest step? Eta times, what the cap on the derivative is delta, right? So the largest step you can take is eta times delta, right? So this guy is going to be, this one is, if I call this whatever, dw is less than or equal to some eta times delta, right? So as I keep stepping through, what can you tell me about this? I equals 0 to infinity. What can you tell me about this? If this is finite, is that a good thing? No? Why not?
Because you may not reach.
You may not reach the solution, right? If the summation at each point, the largest step you're taking is eta I times delta. So after infinite steps, the maximum you're going to go is delta times the summation of eta I. If that is finite, there are some initial values from where you can never actually arrive at your solution, right? So based on this, can you tell me some basic principle for this? What can you tell me about this? What must this be? Anyone? Who was it who said infinity? Yes. You are? Advait. Advait is right. Okay. You want the summation of the learning rates to be infinite. Sally, that making sense? Okay, tell me where I lost you. I want to be able to cover infinite distance. If I'm infinitely off from my optimal point, in the limit, I still want a chance of getting to the optimal point, right? It doesn't mean that you will take infinite steps every time. You're going to stop when you get there.
Okay.
But if you're infinitely far away, you still want to have a chance of getting there, right? That makes sense to everybody? But then what was the other requirement we had? Yes?
So is it the sum that has to be infinite?
Pardon me?
So is it the sum that has to be infinite?
The sum must be infinite, right? Because each time you're taking eta times delta. So over infinite steps, you're going to take summation eta I times delta. If the summation of eta I is finite, then there's a finite distance that you can travel from your initial point.
Are you assuming that your delta is finite always?
Pardon me, delta, yeah, like we said, if the loss has infinite slope, you're not ever going to optimize it anyhow. It's horrible, right? So for any well-behaved loss, you need this property, right? But we also wanted the etas to shrink, because one simple way of saying that summation eta is infinity is to say all of them are the same size. But then that we know means that you're never actually going to get the correct answer. So you want it to shrink. So the second property that we're going to say is that the summation of eta I squared is finite. So the second one means that the learning rates are a convergent series. And the first one says the squared learning rate is a convergent series, which means the learning rates are always shrinking. Nonetheless, by themselves, the absolute learning rate is divergent. This is the property that you want for the learning rates. What kind of eta I would satisfy this? Pardon me? What was it? 1 over t. Okay. So Advait is answering everything. I need somebody else to answer questions too, right? Right now we have a one-man show. But so the optimal learning rate is going to be the t'th step is proportional to 1 over t. This is just at the brink of where, the individual, this is the harmonic series. The summation is infinite, but then the summation of 1 over t squared sums to a finite value, right? So this making sense to all of you? Questions? Yes.
Could we walk over why the summation of eta k's have to be infinite? I missed that point.
Okay, so back to my figure here. So let's say you start off from some point here. At each step, you're going to take eta I times delta. That's the maximum step you're going to take, right? So in infinite steps, what is the maximum distance you're going to traverse?
It's summation of eta i's multiplied by the delta.
Summation of eta I delta. And if you start off infinitely far away,
Oh, I see. Okay.
right?
Yeah.
Make sense? Yes. What is the other question?
Why should sum of 1 over t square be finite?
That is a property of summation of 1 over t squared, is it not?
It's not necessary. I mean, we don't require it here, right?
What is the property of the sum of the squares, or inverse of the squares of the integers?
No,
It's finite, right? And we want summation eta squared to be finite because you want the step sizes to keep shrinking with iterations. But if the strings shrink too fast, you're not going to be able to traverse infinite distance. So the second requirement makes sure that the learning rates shrink with iteration. The first requirement ensures that it still manages to get you to your answer no matter how far away it is. And so 1 over t is kind of the sweet spot where both of these properties are satisfied. Yes?
Yeah, I understood why you need the first property of till it reaches infinity, the summation, but I'm not able to understand why the square of the.
So you still want, so you want you want your steps to keep shrinking, right?
So that,
How do you state that statement? What is the eventually your etas must become
yeah.
infinitesimally small.
But that happens with 1 over t also, right?
Exactly. So 1 over t, the summation of etas is becoming infinitesimally small, and yet it's shrinking. So we are summing eta squared, which sort of shows you that the whole thing is converging.
Eta t to be 1 over t cube, for example, and that also shrinks as you progress.
But then what is summation of it over infinity? Is that finite? Right? So you want to be able to cover infinite distance, but you want it to shrink. Yeah.
I had a basic doubt. If you want to be able to cover infinite distance with learning rate into delta step, you want the learning rate component to be infinity, and that's why we want some.
The sum of the learning rates to be infinity.
Why sum?
You,
Why can't we just take, if it's finite, the sum, then why can't we just take infinite steps and just reach the destination? Why
so
do we want the sum?
wait a minute. If you say summation I equals 1 to infinity, eta I is finite, and then you want to repeat that, how many infinities are you taking?
Okay.
Right? That's still going to be infinity. You're still effectively saying that I have infinite steps and another infinite steps. That's the actual series, right?
Okay, so now we're basically saying that we're taking infinite.
End to end, it's yeah. So what? What is the summation of 1 over t squared? It will be finite. It's not going to be infinite. Yes.
Can we take 1 over root t?
There are many other things. 1 over t is just one of the things, right? It's going to be 1 over t raised to some alpha, where alpha has to be less than 2, and that's going to be, or alpha is going to be something. There's a whole family of functions which satisfy this property. But this is one of the good ones that actually satisfies both properties. Let me move on. Right? Yeah. Okay. Yeah.
So is that sum finite or is each term going?
So the sum of some eta squared must be finite.
Yeah, but I still have the same question that he did in terms of why are you using the eta squared has to be finite.
So you want the etas to shrink.
Yeah.
Right? That's our way of stating that eventually, so if eta shrinks, that property just falls out. I'm not going to prove it. If that property holds, it is going to be finite. In the end, eta is going to be minuscule, right?
Oh, so that's just a way of just saying that you're,
That eta must shrink with iterations. That's the second requirement. The first one says eta must allow you to traverse the maximum distance. Yes. Yeah.
Why does 1 over square root of 2 work? Because like
I can't hear you. Can you repeat that, please? Louder.
for 1 over square root of 2,
Uh-huh.
the square of it is 1 over 2, which diverges.
I haven't checked, so if I give answer, say I give you some answer about 1 over square root of t, I'm likely to be wrong. But there's a whole family of functions that all satisfy this property, series. And any of those can be used for learning rate. Yes, Mona? Yeah, the power of the denominator has to be less than 1 for it to diverge and greater than 1 for it to converge. Just, yeah. 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 Exactly. Exactly. You're absolutely right. Yeah. Okay. So anyway, let me continue. Right. So SGD, the proof is that stochastic gradient descent converges almost surely to a global or local minimum if you have these two properties. The summation of etas is finite, which makes sure that you can get as far as you want. And summation of eta squares, I mean, the summation of etas is infinite. So which makes sure that you can travel the maximum distance to get to the optimum. But the summation of eta square is finite, which makes sure that the learning rates shrink with iterations. And the fastest converging series that satisfies both requirements is 1 over k. But there are other kinds of series that you might have encountered in your homework. You can have the envelope follow a 1 over k. So you can have something like a step function, right? And other such things. And more generally, you don't expect to be infinitely far away from your answer. So the first property is maybe not that important. So if the loss function is convex, SGD will converge to the optimal solution for non-convex losses. It's going to converge to a local minimum. Now, here's an example of how SGD behaves. This is not for a neural network. This is for a k-means clustering problem. Now, k-means is a non-convex problem. So because you have to find the optimal clustering and the centroids. So here is how the algorithm converged in this particular example for 10 clusters with iterations. The green shows you the batch update rule, the convergence of the batch update rule. That's the actual error, the loss. And the red shows you the convergence of stochastic gradient. And there's a vertical bar at each point. What does this vertical bar mean? Pardon me? If you repeat the experiment several times, that shows you the one standard deviation at each iteration, right? And so what do we observe? Is SGD actually getting to as good a solution as the batch? Yes or no? No, right? And what happens across different runs? Which is more consistent, SGD or k-means or batch? Batch. So does this mean that SGD is good enough, as good as k-means, as batch? No. Not really, right? It's converging to a much poorer solution and has much greater variance across runs, but the convergence is orders of magnitude faster. Now, converging really quickly to a crappy solution is not what you want to be doing. So you need some kind of a intermediate. Now, why is this happening? To understand why this is happening, let's try to see the math, but first there's a poll. Or it can be stalled. And when the beep goes off, okay, guys, you're done. So, okay, someone on Zoom, is the first statement true? Anybody on Zoom? Okay, I'm waiting. Yes or yes or no? Is the first statement true?
Yes, it's true.
What about the second on Zoom?
Yes.
Okay. And the third? Also true. What about the fourth? Someone in the classroom, is the fourth statement true? All of them are true, right? Beautiful. Okay. So now let's try to understand why this behavior that we just saw in the example happens. And first I'm going to give you some math. That's because, we're all macho, we like to do math, right? Every single training instance can be viewed as a random sample, right? So the loss computed by every single training instance is a random variable by itself. Now, what is the actual objective of training? What did we want to minimize? The expected divergence. The actual objective that we wanted to minimize was the expectation over x of the divergence between f of x and whatever, the desired function of x. This is what we wanted to minimize, right? Now, suppose I give you a single sample. So what does this expected divergence really mean? What is the meaning of this? So what an expected divergence means statistically is that I have a distribution of x's. If I randomly chose an x from this distribution and I computed the divergence for that x, and I did this infinite times, and I took an average over all infinite samples, that would be the expected divergence over all samples, correct? So this is your x, that's what the expectation literally means. So I have my actual function. I have my estimated function. If I just randomly chose an x, at each point I'm going to get a different divergence. If I take the average of all of these guys, that's my expected divergence. Can you please mute yourself on Zoom? Hello? Thank you. So, but that divergence is also going to have a variance, because if you take each point, each of them has a different value, there's going to be a variance, right? So now, if I have a single x, the expected divergence is e of, I'm just going to call this divergence of x, and there's going to be a variance, which is going to be variance of divergence of x. Now, what this variance means is that if you looked at different points across the input space, each of them is going to give you a different divergence, and cumulatively there's going to be some spread over all of those divergences. That's what the variance really means, right? Now, suppose I chose n data points, x1 plus x2, let me call this xt. If I chose a random set t data points, what is and then I took an average. This is like taking t samples from your distribution, right? And then computing the divergence at each one of these points, and then taking the average. What is the expected divergence for this? What is the expected of the, not the divergence at the average point, but suppose I just computed the divergence at each point, and I computed the average, the expectation. What would this be? This is like saying I take a lot of training instances, and then I compute the divergence at each of these training instances, and I compute the average, the expectation of this average. What is the expectation of this average? I think I confused everybody, but what is thank you. What is the expectation of an average? Is it the average of the expectation, or is it right? If all of these are random samples, right? The expectation is linear. Pardon me for confusing you. I'll just give you the answer. So if I take an expectation over here, if I take an expectation of 1 over t times f of x1 plus f of x2, where f is anything, this 1 over t comes out. That's going to be just 1 over t, right? And if all the x's are drawn from the same distribution, This is simply going to be 1 over t expected value of f of x1 plus expected value of f of x2 and so on, which is simply 1 over t times expected value of f of x, and these will cancel out. Because if all of them are drawn from the same distribution, the expected value of every sample is the same, right? So when I average the divergences at t samples, the expected value of the divergence across all of these t samples is the same as the expected value of the divergence for any individual sample itself. Now, this is what we would call an unbiased. So this term over here, which is the average divergence across all of my training points in expectation, is exactly this guy. So for this reason, we call this, just technical jargon, we call it an unbiased estimator. But then, what do we know about the variance of the sum of a bunch of independent random variables? Anybody remember? Is the sum of the variances. The answer is always coming from that side of the room. So if I block that side of the room, is there an answer from this side?
But doesn't there need to be independent to be the sum?
Yes, and if I chose n independent samples, then the sum of the variance of the sum is the sum of the variances, right? And so in this case, I'm going to find something like this. If I say variance of f of x1 plus f of x2 and so on is simply going to be variance of f of x1 plus variance of f of x2 and so on. This is what you're telling me, correct? So if I take the variance of the average, what is this going to be? What would this be? 1 over t or 1 over t squared? 1 over t squared, right? So this is going to be 1 over t squared, variance of the sum, which is going to be 1 over t squared times t times variance of f of x, if all the samples are drawn from the same distribution, right? Which is going to be variance of f of x over t. So what this means is that if I draw a collection of t samples, compute the divergence at all of these t samples, and then take the average across different runs, the variation that you're going to see is going to be inversely proportional to the size of the set itself. Is that making sense to everybody? Regardless of the fact that I tried very hard to confuse you? Okay. So let's work with this. Now, what we want to do over here is that we want to minimize the expected divergence, right? But instead, we are minimizing the average divergence over a bunch of training samples. But then we found that the expected value of this average divergence is the expected divergence itself, which is why we can use this average divergence over a bunch of training samples as our proxy for the function that we're actually trying to minimize. This is an unbiased estimator. And so the empirical risk is an unbiased estimate of the expected divergence. And so we kind of believe that if you minimize this guy, you're going to minimize the expected divergence too. There's no reason to have this belief. This is religion at this point. But it's a religion we're all going to die by. It's one that's worth dying for, okay? So now, yeah. Was there a question? No. The variance of the empirical risk, the variance of the loss, is going to be 1 over n times the variance of the divergence itself. This two we just saw. So the larger, if the variance of the loss is great, then it means your estimate is going to be unstable. What does this mean? If the variance of the loss is very large, it means that depending on the training sample that you chose, you're going to get a different answer, right? So that's not a very trustworthy thing. You want the answer that you get to be relatively, reasonably independent of the training set that you chose. And so you want this variance to be small. So everyone with me? Yeah, okay. So now what happens? This is, if you're doing batch updates, if you have n training samples, the variance is proportional to 1 over n. The larger your training set, the smaller the variance, the more you believe your estimate, right? But if you're performing stochastic gradient descent, what is the size of your sample? At each point, it's just 1, right? So when you're performing SGD, it focuses on the divergence of a single sample. The expected value of the sample divergence is still, the expected divergence. This is still an unbiased estimator. The real problem is that the variance of the sample divergence is the variance of the divergence itself. The 1 over t factor is missing, which means that depending on the sample you chose, you're going to get a wildly different answer. So let's try to see this pictorially. Math is all very nice, but math doesn't make sense to me, and it doesn't make sense to most of you. So pictures are better. Here's the function that we were trying to minimize. The blue curve is the actual function you're trying to model. The red curve is the function that's captured by the network at this point, right? You want to minimize the shaded area, but we cannot estimate the shaded area. So we choose we cannot compute the shaded area, so we choose a bunch of training points. You compute the average length of those little red lines, and based on the average length of those little red lines, you minimize, you update your function. And when you update the function, then the batch update is going to try to minimize the error everywhere. So it's going to say the function must go up in this region, the function must go up in this region, no, go down in this region, the function must go down in this region, the function must go up in this region. It's going to give you all of that information all at once, right? But suppose I have the same number of training points, but the new set of training points are these guys. What is the lesson these training samples are giving me? That the function must go up everywhere, right? It's not telling you that there is anywhere where the function must go down. Instead, if I had these as my training points, what is the lesson these training points are giving me? That the function must go down everywhere. I have the same number of training instances in every case. But depending on where the training samples ended up, I get a very different lesson from those training samples. What is the fix? More training samples. I can have a whole lot of training samples. And that way, the larger the number of training samples, the lesser the chance that if I change the exact precise set of training samples, the overall lesson I get will be wildly different. So this is what the business of variance means. The larger the number of training samples, the more you can trust the answer that it gives you. That making sense to everybody? Right. Now, SGD picks just one point. If you pick this point, you're going to say, my function is fine. No updates are required. On the other hand, if you pick that point, you've got to say, I have to raise the function everywhere. If you picked this one, you would say, I have to bring the function down everywhere. Clearly, it's not, depending on where the specific point you chose is, you're getting a very different answer each time, which is why across runs, the variation is going to be very large. Whereas for batch, because you have this 1 over t factor, across runs, you're going to have different, much lower variance, which is what explains the difference in the variance in the two cases. On the other hand, so clearly having this, making an update after every single instance is not a great thing to be doing. Yet, you want to get the benefit of the computational benefit of being able to make fast updates. So is there a sweet spot? Can we do something in between? What is that? A mini batch. A batch is the whole thing, right? So here's what we can do. So in summary, SGD uses the gradient descent from only one sample. So it's consequently high variance, but provides significantly quicker updates. So is there a decent medium? Here's what we can do. We can adjust the function at small, randomly chosen subsets of points. At each point time, you keep the adjustment small. If the subsets cover the training set, we would have adjusted the entire function. And as before, you're going to have to modify the subsets that you chose from iteration to iteration. So here, for example, if you chose these 3 points, it's going to tell you to push the function up here and pull the function down at the 2 central regions. And so it'd make an adjustment, and then the next time you'd pick up 3 other points and keep repeating this process. So the pseudocode over here, instead of just making an update after every sample or after the entire training set has been processed, you'd make an update after every B samples, where B is your so-called mini batch size. Now, what is the benefit of mini batches? And what is a good mini batch size? For that, let's go back to pictures again. Oh. So we saw that if this is your batch size, and if this is your entire training data N, and if this is a single instance, then this is the variance of the divergence of X, right? And then as you increase the batch size, what is the variance of the average loss over the batch? It's going to fall down as 1 over the batch size, right? And it's going to go down pretty rapidly till it goes here. And so it turns out by the time you get to a mini batch of about 100 or 128, the difference between that factor, 1 over 100 versus 1 over n, ends up becoming really small. And so you don't really need to process your entire data all at once, although that is in principle the best thing to do. If you process the data in smaller batches, so long as the batch size is great enough that the variance across mini batches is still comparable to the variance that you'd get over the entire training set, then you can get the same kind of benefit. Making sense? Right. So those guys, you still have all the other properties. You still want to randomly permute your input from epoch to epoch. You still want to shrink your learning rate because you're not processing the entire data. But you would be working at mini batches, within mini batches, 1 mini batch at a time. So the mini batch update over here, you're going to be, the mini batch loss is the average loss over the mini batch. And as before, the expected loss, the expected value of this mini batch loss is the true expected divergence. So this is an unbiased estimate. But the variance now is scales with 1 over B, which is the mini batch size, and 1 over B, there's some, yes.
I had a question about the earlier figure that you showed, like between SGD and batch. So I think you said that SGD, it converges at poorer minima.
Yeah.
So I understand why the variance is greater, but why is it converging at a poorer minima if the expected loss is the same?
So in this particular case, again, simply because it has larger variance, you cannot really be assured of where it's going to end up, among other reasons.
So is that just because of the variance?
That's going to be, that's one of the reasons, one of the significant reasons.
Okay.
Right. And so here's what we get when you have SGD versus mini batch versus full batch. The full batch converged really slowly, but the variance is small and you got a good estimate. The SGD converged very quickly to a crappy answer, yes.
But SGD also, if we run it for a long time, it shouldn't it converge to the same way?
The order in which you're processing the inputs is going to change. So yes, there's a theory versus the practice. This is a real practical run. So this is basically the kind of behavior you can expect. In theory, for the right kind of function, SGD should give you the same answer as batch updates. Right? But in practice, it won't. And so in practice, because your loss functions don't satisfy the properties that the loss functions where the convergence of SGD is guaranteed. Now, here's what you have with mini batches. And you can see with mini batches, you're converging as fast as SGD. You're converging to an answer almost as good as the full batch update. And the variance is almost as slow as the full batch update. So it's a It's a kind of sweet spot. Now, measuring the loss, let's skip that. Actually, yes. In this particular experiment, after each update, the entire training data was passed through the model to compute the average loss. In practice, you're not going to be doing that. You always plot only the latest mini batch loss, right? So there's no guarantee of convergence or any kind of behavior for the latest mini batch loss. All properties are for the loss on the entire training set using the current model. So if the plots that you get during your homeworks don't match these, it's simply because the loss that you're plotting is the loss for the latest mini batch or the latest sample, which can be anything, right? Hopefully it still converges, but there is no guarantee. Now, so in practice, training is performed using mini batches. The mini batch size is typically set to the largest that your hardware will support. Larger mini batches mean less variance, but also, yes.
Still a little unclear about where SGD would converge, because the last option of the poll, which we found to be correct, was that SGD will always converge to a global optima if the learning.
No, it's not a global optimum. It'll converge to a local optimum, right? There's no guarantee of global optimum for anything. So it's just going to converge to something, and you have no idea where it'll go. So, and larger mini batches mean fewer updates per epoch. That is also an issue. The convergence depends on the learning rate. So you want it to follow the two properties that we mentioned. Yes.
I couldn't intuitively understand how the expected convergence over any random point is equivalent to the average of all expected divergences over the points.
So what do we mean by the expected divergence? So this one, let's go back here, right? Let's see if I can have the picture. Yeah. So when you speak of the expected divergence, you're saying that if I randomly chose infinite points, computed the divergence at each point, and then I took the average, that is your expected divergence. If I did that in groups, it's still going to be the same answer, right?
Yes.
That's all we mean. Ideally, that is in the limit, right? If I, regardless of whether I chose a single point and then I averaged, or I chose 3 points, took the average, and then did that a million times, the answer is going to be the same.
I see. So the expected divergence over the mean.
In every case, the expected divergence is going to be the same thing. The variance will differ. Right. Now, I am running out of time, so yeah, there is a poll. I'm way behind. Time's up, guys. Okay. Is the first statement true? Yes or no? Can someone tell me if the first statement is true?
Yes.
Thank you. Second one. Third.
False.
What about the third one?
True.
Fourth. The fourth.
True.
The second one is the only one that's false, right? Thank you, guys. So the story so far, SGD, in SGD, you present training instances one at a time. This can be more effective than full batch training. In some cases, provided the data are presented in random order. But for it to converge, the learning rate must shrink rapidly with iterations. SGD estimates can have much greater variance than batch estimates. And mini batch updates, which operate on small batches of inputs, will have lower variance than SGD. The convergence rate turns out is actually theoretically worse than for SGD. In practice, it actually ends up behaving better, right? Also, because we get the benefits of batch processing that we have these days, overall it behaves much better. So that's what we do. Now, one of the outcomes of all of this is, I'm going to go 5 minutes over. I've been too slow. So one of the outcomes of all of this is that you're not looking at the entire data at each time, right? At each point, at each time, you're looking on at one or a small number of data points. What you really want to do is to follow the gradient, which is the average gradient of your entire training data. Instead, you will be following the gradient of your local mini batch or your local sample, which will be kind of representative of the overall gradient, but not really. So this means that your gradient itself is going to be noisy, right? And what we really want to do is to not have noisy gradients. So this is where the trend algorithms that we spoke of earlier end up mattering a whole lot more. Remember what we did with momentum updates? In the momentum update, we maintained a running average of gradients, and then we updated with the running average of gradients. Now, when you're performing SGD or mini batch, this running average is more likely to represent the overall gradient over the entire training data than if you're than in the usual batch case, right? And so it turns out that making sense? So these momentum techniques, which maintain the running average, actually end up being a lot more important when you're performing SGD or mini batch, because you're somehow getting the benefit of considering the entire training data at each update instead of just the latest gradient. And so momentum techniques end up being kind of critical if you're performing SGD. And of course, in the momentum techniques, we saw two different approaches. One was the basic momentum itself, where we just maintained a running average of the gradients and then took a step over the running average. I won't go over it. We've already seen this in the last class. And what was the other alternative? The Nestrov's method. So the difference we said was that in the momentum update, if you had just made some kind of an update of this kind just now, you would first take a step against the gradient, then add in a scaled version of the previous step, and that's going to be your net update. In Nestrov's method, you reverse the order. So that's the two steps, right? First, you take a step against the gradient, then you add in a scaled version of the previous step. And that gives you the new step. So the green step is going to be the one that you'll be using in the next update. Whereas in Nestrov's method, you change the order. First, you took a step in the same direction as before. Then you took a step against the gradient. And that would be the net update. So the next time, the next Nestrov step, you'd be extending the black line and then taking a step against the gradient. Yes.
Does SGD plus momentum have an equivalent performance with mini batch?
SGD plus momentum, that's not a question I can have an answer for, but I would expect it to. Right?
Yeah, of course, but generally.
I'm assuming it would. That's a simple test. You should run it and let us know on Piazza. Honestly, I don't have an answer. I expect it will. Because that's the whole point, right? That when you're averaging over, when you're maintaining momentum methods, you're averaging over training samples. Yeah.
Is it natural just a scaled learning rate?
Not really. So you're modifying the gradient. You're maintaining a running average of the gradient. So we'll get to that in a minute. Okay. So this was Nestrov's method. So this was the difference that we saw. This was the picture from Hinton that I showed you in the last class. First, we agree that the momentum methods are going to be almost critical when you're performing incremental updates. Then second, we see that if you're just using regular momentum, then if you were here, you take a step against the gradient, then add in a scaled version of the original step, which would take you here. In this example, if you're using Nestrov's, you would extend the previous step and then take a step against the gradient. So that would be the net update. Then in the next step, you'd extend this green line, which is this one, and then take a step against the gradient, which brings you to the new one, right? So you can see that Nestrov's method is actually going to be, at least for convex functions, it's going to be far more optimal. And the only difference between what we saw earlier and now is that the gradient that you're going to be using in all of these updates are the SGD or mini batch gradients. So let me skip all of this, right? Now, so moving on, what did the momentum method fix? What was the point of the momentum methods? So what was the term we actually corrected? The gradient is what we fixed, right? The gradient estimate was supposed to be noisy. So you smoothed it out using running averages. So in the update rule, that term was the term that you fixed, right? But there's also a second term, which is that. This learning rate, right? What can we say about the learning rates? We saw that ideally you want a different learning rate for every component. We also had these other principles about how the learning rate must shrink and so on. But still, what is the best schedule? For that, can we actually look at the data itself and decide on the fly? Now, let me give you a couple of examples. If I'm just considering the running average of the gradients, I have 3 examples over here. In each case, the arrows show you the direction of the gradient step at each iteration. In all 3 cases, the average gradient is the same, right? Which of these 3 is the most stable? The one to the extreme left, right? If you wanted to have a learning rate, in which of these 3 would you assign the largest learning rate? The one with the smallest oscillation, right? So in other words, you want to actually inspect the learning rate, the oscillations in the gradient, and you want to assign your learning rate based on the oscillation of the gradient itself. And so you want to, so how would you do that? Any suggestions? Yeah. You can capture the variance, or the second moment more generally, right? And the larger the second moment, as you can see immediately, the smaller the learning rate must be. And so I have an example over here. I can just skip the example. You want to have a learning rate that is smaller when the second moment is larger. This technique is what is called RMS prop. So RMS prop focuses on the learning rate, not on the gradient. And so in RMS prop, you look at the second moment of the derivative independently for each direction, for each component. I have some notation over here. I'm going to, you have the derivative, the square of the derivative. I'm going to just write it as partial squared d, where d stands for divergence, right? This is not the second derivative, it's the square of the derivative, just to be clear, just for, I'm simplifying notation. And then of course, the mean squared derivative is the expected value of the partial squared, which is the expected value of the square of the derivative. This is the, so this is the root, this is the mean squared value. If you took the square root of it, it would be the root mean squared value. And in directions where you had a lot of oscillation, you'd expect this to be large. Yeah.
How do you combine this with the conditions that we described over there?
I am not able to hear you. Can you speak up?
How do we combine this with the conditions you described over there?
We don't. They're kind of independent, right? So again, even with those conditions are not a guarantee, except if the function is convex. So we have other issues too. So yes.
The square derivative is computed over the entire mini batch, the average of all.
For the mini batch, right? At each time, just as you know, your momentum method is averaging the, maintaining a running average of the mini batch, or if you're performing stochastic gradient descent, the latest instance, right? So also the squared derivative is going to be considering the derivative of the mini batch. And so here is what you would do. You would maintain a running average of the squared derivative. The running average at each point is going to be some gamma times the current running average plus 1 minus gamma times the square of the latest estimate of the derivative, right? And so you would maintain a running average of this square derivative. And the learning rate, you'd have an initial learning rate, and then you're going to divide by the root mean squared value of the squared, the RMS value of the derivative. So the greater the oscillation, the smaller this is going to be. The smaller the oscillation, the greater this is going to be. You're sort of automatically learning the optimal learning rate at each point. And this is shown to behave really, really nicely. So we've seen 2 things, right? We've seen 2 different solutions. One is how you can fix this guy by maintaining a running average of the gradients. And how you can fix this guy? By maintaining a running average of the squared derivative and using the inverse RMS value as a proportionality factor for the learning rate. But these are two independent things. Can we not combine the two? You'd expect that you can combine the two as well, right? That's the obvious next answer, next step. And so, by the way, so this thing is called, when you just have a learning rate which depends on the inverse RMS value, this looks a lot like R prop. What would happen if the derivative were always constant? If you had a slope, a plane, what would happen? Is the RMS value going to be different from the derivative itself? The magnitude is going to be the same, right? The two would cancel out, and you're only going to be taking steps based on the sign of the derivative. That's like R prop. So that's why they call this RMS prop, which is an extension of R prop. It's an adaptive version of R prop. But anyway, RMS prop only adapts the learning rate. Momentum only smooths the gradient. So let's combine the two. And when you combine the two, you get this technique that all of you have been using called Adam. So here, you're going to do two things. You're going to maintain a running average of the derivative itself. That's X. So that gives you an expected derivative over all of the batches that you've had so far, right? And you're going to be maintaining a running average of the second moment. Now, there's an extra bit of heuristic over here, which is the 1 over 1 minus delta raised to k. I won't get into the details of it because I'm out of time. But basically what happens is that in the early iterations, if you initialize with 0, this can lead to a behavior where nothing ever changes, because running averages of 0 basically are going to be very small, right? And so but the basic idea is this. You actually maintain a running average of the derivative, and you maintain a running average of the squared derivative. And the actual update rule over here is going to be same as before. The update is based on the running average of the derivative for this gradient term and the inverse RMS value for the learning rate term. This is Adam, right? So is this making sense to everybody? What we've done so far? Yes. Ask me about the delta and gamma on Piazza. I'll explain because I want to get done on time. So there are other variants of the same theme, add a grad, add a delta, add a max, but the basic idea, the two components that we just saw, that's all you really need to know. The rest of them are various kinds of finesse, and they don't really buy you very much. And so there's one poll, and then I'll take a minute more. Hands up, guys. Okay, can you quickly tell me which of these are true?
All except first.
All except the?
First.
Thank you, right? We don't need to go through it. I'll just quickly sort of go through a couple of examples that Alec Radford has on his webpage. So this is Beal's function. And Beal's function is this crazy looking function out here, which has a which has a minimum out here in this dark blue area. And it shows how different functions, different optimizers behave differently. Now, standard, in every case, you will see that standard SGD, which is the red curve, takes its time getting there. The momentum method sort of swings around and then eventually gets there, right? RMS prop Do they have RMS prop, which is the black one? Sort of gets there eventually. And the fastest one in all of these, even if although Nestrov's method actually starts off swinging a little more wildly, it eventually just gets there. Now, the behavior on this particular function is not so telling as this one. So this is this nice saddle-like curve. And you can see how the saddle-like curve, eventually the slope becomes almost steady beyond the minimum, right? And so SGD sort of oscillates around, finds a flat region, it's happy over there. There's nowhere else to go. It's done. But then momentum. Wow. Okay. If you can't hear me too bad, we're done. So, but momentum also sort of, I think, gets stuck in that central region, or does it? It actually comes out. Because after a while, it figures that all the little, these things cancel out, but in the other direction, it eventually sort of builds up and goes, it travels down that way. If you look at RMS prop, the slope eventually becomes uniform, which means the RMS prop is not really speeding in any direction. It just continues, it travels in the horizontal direction for a while, but then quickly figures out that it has to go down the slide, but then it stays there steady. It doesn't really speed up, whereas Nestrov's method, and if you add Adam, both of them would sort of speed down to get to the solution. So you can actually visualize the loss function and inspect how things will behave. And here's another one. You see the same kind of behavior, that it's going to find a value and go down. Right? Anyway, so the story so far, just adding to the one last point, convergence of all of these various incremental update methods can be improved using smooth updates and adaptive learning rates. One final thing, the nice thing with using something like Adam or RMS prop is that you do not have to worry about learning rate schedules. The algorithm automatically figures out what the optimal learning rate is because you have an initial eta, and the manner in which it must be scaled is figured out based on the behavior of the algorithm itself. So they are a definite advantage over other techniques which need schedulers. Not everything works everywhere, right? So we'll stop here. I'll take any questions on Piazza. Thank you for coming. See you next class.